We're going to update the link. You can already enter the link in terms of the website tutorial, but slides will be updated once all the reference will be there. So yeah, sorry for that, like just 2-3 days. All right. Given the previous slides and what we talked about, we kind of have knowledge more or less what is there up in terms of the data or how we can gather data from scratch on our own. Now we can move to the more important part for all of us, which is modeling data, modeling dialogues. We will be talking basically from 3 perspectives. It's going to be end-to-end learning. That is kind of an academic, currently sexy approach. We then talk about retrieval dialogues that could be also seen as an end-to-end, but for the sake of this tutorial, it will put it in a way. And finally, Iñigo will finish of our thoughts. How can we possibly start converging in terms of academia versus what's happening in industry? So I will start from end-to-end learning. And going back to this modular perspective, as was previously stated, that's been a core of all dialogue systems, and it currently is for most of the deployments in real life. It's highly modular, and there is no much communication between the modules in terms of resharing the knowledge. Of course, from a research perspective, but I guess in the long term, we would love to see something that is more combined together in terms of the structure. For obvious reasons, in terms of maintenance, for example, it's way easier to maintain one big neural network or a couple of neural networks, but still combined in one file, rather than talking to different modes where you also have to set at least some APIs between them. In terms of the whole definition of it, as we said previously, saying end-to-end, what I mean by end-to-end is end-to-end for task-oriented dialogues. So a lot of people can start saying that, well, just calling third-party APIs is completely break the differentiability in this learning. I completely agree. But for the sake of this tutorial and what's happening in terms of nomenclature, at least for task-oriented dialogues, as long as you have more or less communication between neural models of these 3 parts, which is language understanding, dialogue management, response generation, if you have this communication, you can still, most of people call it end-to-end. And most of the time, if you see end-to-end, that basically also means that the response is being generated rather than retrieved. Although if you think about it, if you have neural network that at the end of the day does all the same stuff like language understanding and dialogue management, but retrieve the answer rather than generate it, it's also end-to-end. But it turns out that in academia, actually, most of people, when they are working on retrieval, do not call it end-to-end. So. Going back to the question, why end-to-end? Well, faster retraining cycle, just because you have one model, theoretically it should be way easier to productization should be way easier. Because you don't have to talk to different models and updating one sometimes more often than less often actually is also very harmful for other parts. Here we should avoid that. By definition, it's a natural framework to share the knowledge. Why belief trackers should be separated for policy management, right? These 2 components should be combined together so that we easily pass both information from each other. This is not happening in Modular 1. Theoretically, less sophisticated annotation schema, because we're trying to avoid explicitly training some modules that were always there in classical approach, right? And again, theoretically, we should take advantage of online conversational resources, because at the end of the day, what we would like to have is just to basically putting inside our neural network some conversation and getting our ready to productize model out of it. There's a lot of cons against that, but for the sake of it, let's not think about it for now. It's easy to see them straight away when we start talking about it. So going to the actual models, I guess seminal work starting with Tsung-Hsien Wen.
that basically was a copy of standard modular network, modular approach, but putting everything into neural network. So what happens there is to basically using RNN to encode user intent, the sentence and creating the vector of the intent, was training belief tracker that needs to predict what kind of slots or end values really user mention in the given sentence, and carrying them all along the history. And given this two things, we can also query a database. In this case, it was a SQL query that gives back some answer, for example, a number of entities that current query satisfies. And this goes back to the so-called policy network that combines these three sources of information to use another RNN to generate the network. At this point in 2019, it's not really that crazy to think about that kind of model, but 3 years ago it was pretty amazing that one simple model could do stuff, and as we see soon in the results, was actually better than handcrafted stuff. What is also great about this work, highly recommend to read the paper, is that it was actually implementation of Wizard of All Scale collection and bringing it back to research with Cambridge CAM 676 data sets, so it was just around 700 dialogues. But it gave like a foundation for next work. So if you think about the results, well, you can of course argue what was behind handcrafted, which is ADC, what was behind handcrafted dialogue system, but from the perspective of both satisfying the success, thus here is the subjective success of the users who were talking to both of dialogues. They were not only were saying that, of course, a neural dialogue model was more natural than handcrafted one. We could expect that just because the answer were not handcrafted, but also even in the success rate, we obtained better results. So that was great information, and at least worth pushing the research in that direction. Putting on hold the question how easy is this to make the product out of it with real users. Around the same time, there is a Facebook AI paper created by Anton Bord and, if I remember correctly, also Jason Weston, and even already mentioned that the baby dialogue tasks. So what they did was implementing just general sequence to sequence without any modules inside of any sort except for memory networks. And that was a good lesson to learn that if you look at the performance, I don't know where they get the rule-based system from, because the kind of their challenge was the STC2, but the 33 should be way higher. But more importantly, memory networks was performing around 40% of the time properly as they should. So it was a nice message showing that we're not really there in terms of what kind of structure we should use to at least even solve one domain, which is booking a restaurant. Going from that, again, as we said previously, it's not a huge overview of all works that has been done. I'm going to choose all the papers I found really cool, how to push the frontiers. So 2 years later, Lei and with colleagues at ACL last year published Sequicity. I love this paper because basically it was throwing all the way all those subnetworks and just using RNNs. So what happens here is that given the dialogue, we again encode the user sentence in, and given the context, RNN is going to output the prediction of what kind of a belief state we are currently in. Given that, we can query again the database. Given this, the results of the query, we combine it with the belief trackers, and we have another RNN. It could be LSTM or anything you want, and answer the give the final response. On top of that, using pointer network. So not only the structure is way simpler, but if you look at the number comparing to original NDM, the results are slightly better in both of success rate, blue score, and match rate. On a side note, when I'm talking about match and success, match rate basically informs that whether we found the entity that user was looking for. Success rate means that given we give the proper entity, for example, back to the user information, we also satisfy all sorts of things related with the particular entity. Also, really nice stuff. If you look at the time of training, we basically there were different frameworks to argue how valid is this number, but it was around 10 times faster to train, which from product point of view is super important too. If you look at also closely at the table, the results with reinforcement learning, we're gonna go back to these numbers a little bit later when we're gonna move from supervised learning to reinforcement learning, at least for end-to-end modeling. Another really cool work coming from Tony Tao with colleagues again in ACL last year. So basically what happens when we start doing end-to-end modeling is that we are losing explicit modeling of what we used to have, which was belief tracking and defining the slots and values inside, as well as policy management. Back in modular models, we always have this actions or intents that we start from and then operate on. In end-to-end one, we just get most of the time input in, input out. So in this work, unsupervised discrete sentence representation learning, what was the aim of the work was to create basically latent space that was trained in a way that could capture these intents in an unsupervised way. And there was two requirements that the intent should have, if you think about it, is that Z should, C here is the context, X is the answer of the system, Z is the latent vector inside. Z should capture the most important part of the features of the response. We don't really care about the A or commas, but we do care about that the most important semantical information is there. And second of all, might be not straight to think about it, but Z should actually be independent of the context, in the sense that you should not define the representation based on the context, but this should be in more way abstract, but of course then you will choose Z based on the context. So how to achieve that? First, they started with training the so-called recognition network and generation network using variational autoencoders with some funky stuff in terms of doing elbow in better way. But once you have that, the trick is that once you have the recognition network, you can define a policy network that given context was learning which Z, which latent intent choose from. So in that case, we are satisfying requirement first. And given this intent, we can also predict the whole sentence, which is the policy network. I'm not going to show you any results in terms of the hard numbers because the data sets that were used in the papers were not really task-oriented. But what is cool, if you look at here, is that in completely unsupervised way, these both models that were mentioned here could find a more general latent spaces like scheduling or requests that truly were then were translating when you generate sentences to something that was more or less constant. Of course, I can find a lot of examples where this didn't work out, but again, it's pretty hard job to do. Moving forward in terms of the problems with end-to-end, these nasty databases. So one might ask ourselves, actually, why do we even talk about it? But if you think about task-oriented dialogues, I can really see example where you cannot, well, you don't have to use any sorts of knowledge base that you can really easily incorporate into your model, right? Most of the time you will have to call third-party APIs, whether it's booking of the hotels or finding some useful information for the users. So what can we do about it? It's hard because querying the databases basically breaks differentiability. It's some things that you don't control in terms of your model. but it's necessary to put in. And there's been some works to break this hard lookup and creating a soft lookup approaches. And starting already in 2016 with Dringa and colleagues published in ACL, the very clever and simple approach in the beginning was to basically create the priors over your database. So for example, your prior might be how many times values in specific slot were mentioned, and combining this with also your belief from belief tracker, what kind of a values user is currently thinking, you can create the posterior that you put along with the belief tracker into your policy network. So what you could do then is that you train your whole model end to end, and when it comes to providing information from the entity, you just sample from this posterior. Because it's probabilistic, of course, it's not 100% reliable, but at least you don't break differentiability. What is also cool is that if you look at the numbers, they started with rule-based policy, then they added reinforcement learning, and on top of that, they forget about the rule-based, but trained completely end-to-end model, and worked better than the hard KB information that we're getting, or no KB. That's of course results. That was pretty simple way to approach that. If you don't know the answer, when you know the answer, how to do it, and then really nice stuff coming from Erich and colleagues at Sigdal 2 years ago was moving a little bit more to kind of putting attention over your database. So what they did was to create a series of triplets. So that basically, what you can do, you can encode the sentence that was coming from the user, and while generating the words from the system, you start basically matching the next hidden state with all the possible triples that you have in the knowledge base. And given the context, all these scoring things, you decided whether to use normal vocabulary, which is normal words, or all these triplets in canonical way. And this again is fully differentiable. Another side project that was related with this paper is that they presented a really nice multi-domain data set spanning for over 3 domains with 3,000 dialogues. And quite amazing is that the proposed project was pretty okay if you look at the human performance. What's missing here is that the actual dialogues are pretty simple, is around like 3 to 4 turns. So the task was not that hard, but again, full end-to-end approach. And really good results. Finally, in terms of incorporating the knowledge bases, Madotso with colleagues last year ACL used this time multi-hop attention, where you put in your memory both the dialogue history and also the knowledge base. Given this, you basically do recurrency over what words to output, and again, using the pointer network and attention, you decided whether to use normal vocabulary or the stuff from your memory. In this case, results were not better than key retrieval network. However, just comparing to the pointer network, we see that better structuring of your model can give you a huge boost, which is takeaway lesson here. At this point, one might say that what's the point of putting everything from the knowledge base into end-to-end model? And I agree this is a very valid question, but we have to, I guess, push frontiers here, at least where we can. And if you think about it, of course, you can put huge databases inside, but if you think about really domain constrained models, that's already doable at this point. I can't, talking about databases, another thing that kind of breaks differentiability, but is super important, is to grounding your task-oriented stuff into the text. What you can imagine here is that, for example, you're looking for a restaurant, but this time you have for example, Yelp in your backlog, finding some reviews from the user. We're going to go back to it. Actually, Iñigo will go back to it, how you can build this model with Retrieval, from how we actually do it at Poly. Here, for example, a seminal work from Gazvini Najed was to combine still classic retrieval stuff to first find the world facts, and matching it with the conversational history to find contextually relevant facts. And that's basically most of the knowledge-grounded neural models work in the way that you encode your current dialogue history, you encode the most important facts that you retrieve in IR fashion, and you do kind of a playing around with these both encodings to find the best answer and to generate that. Not surprisingly, in terms of informativeness versus pure sequence-to-sequence model, we got way better scored from human subjects. Another great work here was presented last year in EMNLP by Dinan and colleagues from Facebook, where they showed how, again, very nice in Wizard of Oz fashion, you can get Wikipedia conversation where one of the wizard was the guy who had the information about, for example, one article, and then the user was trying to find important stuff from the article. From the modeling point of view, it's 2018, so they applied transformer encoders, both for encoding the knowledge and the coding. More importantly, if you look at the results, actually you see that the boost for the generative models, because they were building both generative and retrieval ones, is way larger than for the retrieval ones. Which is kind of an interesting observation, and I'm not really sure what's going on behind that. But given the knowledge, the generative model was substantially rated better by human subjects. And overall, we're still far from satisfying the human performance, but it's definitely a step forward. Jumping on for another problems that is happening in end-to-end community right now is the reinforcement learning for fine-tuning. In last couple of years, we were used to building basically from scratch dialogue policy through reinforcement learning, thanks to better data collection pipelines or reusing data from internet. This kind of a scenario change where RL is used as fine-tuning. Also, it's important to start thinking about RL for many reasons, because most of the end-to-end models trained in just supervised way train something that is completely different from what your user expects. What I mean by that is that most of the time we're training against log likelihood of whatever you have as a loss or blue score if it's open domain. But what you really care is actually satisfaction of the user, which we sometimes translate, for example, to the success rate. And this can be done through RL. And on the second important part, you can really translate that long-term planning through SL if you don't have enough data, but you can enforce that thanks to the RL loss. And these two main things that are great to basically fine-tune your model, as we're going to see with the next models. How do we do that? Most of the times, most of the works employ policy gradient methods. It's pretty straightforward algorithm where given your reward, for example, completion task, you skew your policy, which is the probabilities of choosing the action A given the state S to the place in the space where you'd like to be. Again, seminal work here was by Tsung-Hsien, 2 years ICML. Again, here a belief tracker was trained with sub losses, but most importantly, he introduces a policy network where because of you have to choose policy, you break differentiability, but RL is going to help here to rescue. So again, the architecture is pretty similar to original neural, models trained with supervised learning. But because of sampling the action, we break the differentiability. So what we can do here is to introduce RL finding procedure, and it works in the following way. We first train in a cell all the modules of the network here. Then we freeze all the modules except the policy network. I'll discuss that later, why we're going to do that. For each RL episode, we just get the sample of batch dialogues from the training set. We are running every dialogue, but this time we allow the modeler to choose from the new policy, keeping the answer of the users the same. And we compute the success rate, basically, whether we satisfied the user needs in the given dialogue. Given that, we can update the parameters through policy gradient. If you look at the numbers, not surprisingly, what we care about, which is the success rate, goes substantially up. And there was additional work done by where he was trying to figure out what kind of a policy space, the size of it is the best. But main takeaway message is that RL can boost the metrics that you really care about. Related with that is Tony Tao and colleagues' work from NACL last year, where back when 2018 was pretty common for open domain dialogue systems to use RL on the level of words. Again, here re-emphasis is that we should be thinking about putting this signal on the level of actions, which used to be that way when we had modular model. And again, going back to the sequicity model that I mentioned, when they were mentioning RL, they were actually training RL using words signals. Here we're going to use action levels. So if you look at the numbers, again, there is no surprise that that's the results. The success rate is trained on multi-was is way higher than the baseline, where it's just natural model trained in a supervised way. But also it comes at the price, because freezing your policy is susceptible to the overfitting, and you can see that on the perplexity and blue score, where basically your model is trying to use the keywords rather than speak really nice syntax. Primarily this happens because we still operate in ridiculously small dialogues data sets. But it's going to be true even if you're going to have more data, but especially painful if you're working on even just 10,000 dialogues. Finally, I cannot not mention what's happening right now in terms of pre-training. I guess everyone started working on that in the last 2 years full-time. This is also true for dialogue systems, especially for end-to-end and retrieval ones. It also started being used in task-oriented fashion. So why is that? Because, of course, gains are huge. First of all, it resulted in paradigm shift across the whole NLP industry, and it's true also for task-oriented dialogues. But it has been proven that it's good for dialogue modeling, end-to-end one. And ironically, I talk a lot about the data scarcity problem, but it could be a final nice way to deal with that, in the sense that pre-training offers you to learn about grammar and syntax, for example, of the language, leaving you with the problem of figuring out for example, dialogue reasoning that you need to solve with, hypothetically, way smaller amount of data that you would need if you would have to learn that stuff all along the way. So how does it work on practice? We use transfer to lately architecture proposed for persona chat for open domain dialogues, where we thought we were thinking how to reuse, for example, GPT knowledge into more task-oriented stuff. And what we aimed at was to create the approach where text is the ultimate input, and you can achieve that by literally putting just an sequicity but in a more explicit way, everything as a text. So here would be literally defined that there was a belief state of restaurant with some slot and values along how many domains satisfied current query of the user, and given the dialog context, you just feed it into GPT and fine tune it on your specific domain. Unfortunately, we did not get really big gains against the baseline, but given the amount of modeling that basically creating the whole pipeline was just a couple of hours, is a huge gains in terms of easiness of building this stuff. Great work by Mehri from ACL this year was pushing forward how we can evaluate whether pre-training is really helpful for us. And if you consider like for following pre-training task work, for example, you have to learn how to use next utterance retrieval, then you need to learn how to use how to generate the next sentence. They also define mask utterance retrieval, where you put fake sentence inside in both tasks 3 and 4. And if you consider these things as a pre-training tasks, and then you can ask yourself how these pre-training things might help me for belief tracking, which is BSP, dialog act prediction, which is DAP, neural user retrieval, and next user retrieval and next user generation, you can see a huge boost, for example, while pre-training your first model to generate and then retrieve, which is in some sense sounds illogical, and this change is even more visible when you pre-train your models on full data, but then you train your final models on 10% of the cases, and the gains here are even higher, which proves that the theorem that pre-training really helps to stabilize training even in a small size margin, small case of the data. Pushing forward the numbers, recent work from Wu and colleagues was reusing again GPT with clever memory recurrence and modeling independently user and system input. Not going to the details, they start matching basically well fine-tuned models on multi-was, also in terms of informant success rate. So adding more better structure with these, for example, GPT can really get you far in terms of model performance. So we can ask ourselves how we're doing in 2019. Well, DSTCT8, as we mentioned before, had this multi-domain dialog task completion challenge based on multi-was, where you were asked to train end-to-end model, well, whatever model, but most people were doing end-to-end modeling on multi-domain conversations. And if you look at the numbers in terms of automatic evaluation, we are almost there, because success rates is almost 90%, with really small number of turns. It's only 7. But the reality is a little bit different, because what we care about is the human evaluation. And if you look at the final results from top 2 models, the success rate goes down to only 68%, while the number of turns soaring up to 20, which is a nice information that something the way we're modeling is still way off from what we have as our evaluation versus what human thinks. And this is general problem with evaluating dialogues in both for task-oriented and open domain. As I said before, I did not cover even 10% of the stuff that's happening in this field. So just a couple of other words that are definitely relevant. And on that, we're going to switch to retrieval-based dialogues.
Thank you. Hello again. So I'm going to talk about retrieval-based dialogue. So what is exactly retrieval-based dialogue? So first I will talk about what are the problems that we have now with end-to-end systems. So these systems need to do a lot. First of all, they need to encode the meaning of what the user has said and potentially all the dialogue history. Then they need to implicitly select the action or the response that they are going to take. And then they need to get this representation of the response and generate a set of symbols, a set of words, which is going to be the natural language response. Well, this is basically a lot to do, a lot to learn at the same time. So what if we skip the generation? And basically this is the main idea of dialogue as an information retrieval task. So basically first, we predefine a set of all possible responses that our dialogue system is going to be able to take. So for example, like you can see in this example, like any kind of set of responses as big as you want. And then in the second step, given the context, given what the user just said and all the possible dialogue history, you will just select one of these responses, and this is what you are going to show to the user. So this way, you are skipping the last part, the generation part, and it has many benefits. So if we compare generation-based end-to-end system to retrieval-based end-to-end systems, obviously the generation-based systems are going to have a much more variable output, because basically in retrieval your output is constrained by the list of candidate responses that you have predefined in the beginning, which in some cases it can be good because you won't have kind of any surprises. You don't want that your system, for example, says something politically incorrect or insults the user or whatever. So this is the first difference. As we have seen before, generation-based systems are very prone to give kind of like very short or general or irrelevant answers, so what is kind of known as the I don't know problem. Well, with retrieval-based system, you can basically define your answers to be informative, semantically relevant. So you know that you will never select this kind of uninformative answers. And as I said before, if you include generation in the end-to-end training, this is another module, a kind of difficult module that it needs to be trained jointly with the rest of the system. What in retrieval, you're already predefining the set of things that you are going to say. You don't need to learn to do generation. Therefore, the system is easier to train. So even if retrieval-based dialogue has been around for quite a short time, it was just proposed a few years ago, it has been a lot of interest in the last years. And actually, I have been only working on it for a little more than 1 year, so I'm not an extreme expert on it neither. So this tutorial, or this part of the tutorial, is going to be more focused on explaining what's the idea behind all these systems, rather than doing an extensive review of all the work that has been there during the last years. So I apologize if I miss any important citation or so. So basically, how do all these retrieval-based dialogue system works? They work over something that we call the neural response selection model. So basically, in each turn, we are going to select one answer or one response with a neural response selection model. How do all these models work? Basically, we will have two inputs, two sequential inputs. In one side, the context, which is going to be the last user's turn, plus potentially all the previous dialogue turns or whatever, and even you can augment it with other kind of data. And we will have the response, which is going to be one candidate from one natural language response, like any kind of example. Then these two inputs are going to be fed into a neural architecture. Anything, the only thing that these things need to do is somehow reduce these two sequential inputs into a single score. And this score, what it's going to tell us is how well does the context match the response. So basically, if the score is high, it will mean that the response makes sense on this context, and this is appropriate response to this context. If the score is low, it will mean that the response doesn't make any sense given this context. So how are we going to train this? During training, it's kind of very straightforward. We are going to have pairs of context response pairs. Some of them will be positive examples, basically the context and the response match, and some of them are going to be negative examples. Will be a context with a randomly sampled response. And basically during training, what we are going to do is we are going to maximize the score of the positives while minimizing the score of the negatives. How are we going to do inference? Well, as I said before, in the dialog system, we are going to predefine a set of possible responses. You can do this in the beginning of the dialog system, or you can have a pre-processing step that kind of like reduces the set of candidate answers to a smaller set. And then what you are going to do, sorry, I don't know if this is too loud. What you are going to do is score one by one all of these candidate responses, and basically the one that gets the higher score is going to be your response. You are going to show this to the user, and you are going to wait for another turn. So what do we have inside of this huge block that I called the neural architecture before? Well, as I said, it's anything that can reduce a sequential input into a single scalar, into a score. So any kind of neural architecture that has been around during the last years that can do this has been used. Like, for example, DNA pooling, recurrent neural networks. Obviously, the last couple of years, transformers have been very, very popular. As I said, you can just do the response selection based on the last turn of the user. You can concatenate all the dialogue so far. You can combine hierarchically the different turns and so on. Then there are like kind of two main ways to get the score. There is like the dual encoder architecture, in which basically the context and the response are kind of encoded independently until the last scoring step where the score is computed, while fully connected models, basically, yeah, the context and the response interact with each other from the beginning of the neural architecture. And now I'm going to very quickly review some of the papers that have been presented in the last years, which show differences between or examples of these kind of different neural architectures that I have been talking about so far. So this is one of the first papers that was presented. It shows a dual encoder architecture because, as I said, Yeah, as I say, we can see that the context and the response are encoded through different paths without any interaction between them, and in the end there is a score function that basically tells you how good is the match between the both of them. Basically, in order to reduce the sequential input into a single vector representation, we use recurrent neural networks to kind of roll in the representations. Then the universal sentence encoder is another example of dual encoder model, in which in this case we kind of have like a shared encoder or some shared structure that encodes the input and the response using the same weight, the same structure. After that, we have, let's say, a few feed-forward networks that basically kind of transform the response representation, the natural language representation into a response representation, and then we have a dot product for scoring in the end. Basically, inside these encoders, as I said, we can have any kind of way of reducing a sequential input to a single vector representation. In this paper, they propose either feed-forward networks with average pooling or a set of transformer layers. Recently, they have also presented multilingual use, which is a very interesting extension of this work because they don't only train it on response selection, but they also train it on, let's say, on translation matching. So basically, they have a set of candidate translations, and they have to choose which is the correct translation amongst this set. And this actually permits training a neural response selection model that works in cross-lingual response selection. So basically, maybe you can ask a question in Spanish, and it will find the relevant response in English, if it is in there. This is an example of a, let's say, what I call a fully connected model. Why? Because this model, what it does, it reduces the context and the response through many layers of different kinds of attention. But eventually, before the scoring functions, there is, let's say, there is interaction between the context and the response. So basically, what it does is in here, it just passes everything through more layers and attention, and in the end, it will have a classifier that is going to tell what's the score. this work is I think it's the winner of the Dialog State Tracking Challenge 7 Task 1, which was basically a response selection model in which, again, it's a fully connected model. There is interaction between the encoding of the context and the response in the initial layers, which eventually they go to a binary classifier that basically is going to tell either the score is going to be a binary score that tells like if the response belongs to this context or not. There has been recently also some work in hybrid models, which basically try to combine retrieval and generation dialogue models in order to kind of get the best of both worlds. So basically, the controllability of the retrieval-based models plus the variability of the generation models. And one of the kind of more exciting things about retrieval-based models is that maybe in small systems, maybe just to some extent, but they have already been deployed in industry. There are actually examples which actually use these models that are out there and people is using and working. I think like the most famous example that probably all of us has used is the smart reply system of Gmail, which might be a very simple dialogue task, but this is still a retrieval-based dialogue task that it's there being used by millions of people every day and still working. There are also a couple of chatbots, one from Alibaba and one from Microsoft, Alimi and Xiaoi's, which also in some extent use retrieval-based system and also have like a decent set of users using them. So how do we evaluate these systems? Well, as everything in dialogue, it's not very clear how to do the evaluation of this, but the more used or the more widely spread evaluation method is 1 out of n accuracy. What does this mean? We are going to sample, we are going to get a question answer pair, and we are going to sample so n minus 1. So imagine if we are doing 1 out of 100, we will sample 1 question answer pair and 99 random responses. And we are going to see how often our model finds the correct one, the correct response, out of these 100 responses. And in order to train them, as we have seen some of the models training just with a binary loss, so basically they just treat it as a binary classification problem in which you will give them a question response pair and you will decide if the response belongs to this context or not. Other models, what they do is they go further and they get a loss function proportional to the 1 of n accuracy. So basically, they will get a batch-wise loss in which basically the model every time will try to maximize the probability that the correct answer in the batch is so maximize the probability that the correct answer in the batch while minimizing the probability of all the 99 incorrect ones. So obviously this kind of loss, the larger the n, the better the loss, the more informative it will be. Basically, if you have more, let's say, challenging examples to discriminate from, it's going to be much more difficult for the neural network to find out what's the correct one. So basically, we'll need to find stronger clues stronger semantic clues between the context and the response to be able to work on it. The problem is that some architectures can handle very large ends. And why is that? Like, for example, when I talked before about the fully connected models, the problem of these models is that the context and response embeddings or representations that we get before the scoring functions are conditional to each other. So basically, if you want to score, let's say, 1 context versus 2 responses, you cannot just pre-compute the embeddings of the 2 responses, compare it with the computation of the... Sorry, what I wanted to say is you cannot just compute once the context embedding, compute the response embeddings and get the score of them, because the context embedding is going to be depending on the responses. So you have to do this computation in this case twice. If you do it for a 1 out of 100, you will have to do it 100 times. Instead, dual encoder models solve this in a very elegant way. So dual encoder models, as I said before, they work in a way that the input and the context representation are totally independent of each other until the scoring function, which is actually, for example, just in this case, is just a dot product. So there are not learned weights in the scoring function. Why is this good? Because basically what we are going to be able to do is, if we want to get, for example, a 1 out of 100 loss, we will be able to get a batch of inputs, get a batch of question context response pairs, compute all the embeddings of the inputs, compute all the embeddings of the responses, and then as the score for each of the responses for each of the contexts with its corresponding response is the dot product between them, we can just do a matrix multiplication of all our stacked encodings of the context and our stacked encodings of the responses. And basically our loss function is going to try to maximize the diagonal, because the scores in the diagonal mean the correct matching between question and response, while minimizing everything else. Why is this good? Because this is extremely efficient. So basically this is just a simple, it's a fast matrix product, which we don't need to recompute every encoding for. So basically, we are going to do it in linear time instead of doing it in quadratic time. And more importantly, this is very efficient in GPUs. We can just get a batch, put all this compute all the encodings, do this operation in a single GPU, do this multiplication in a single GPU operation, and we will get the loss for the whole batch. Basically, the limit is, as I said before, the longer the n, the more informative your loss function is going to be. So basically, the limit is on the memory of the GPU. For example, some encoders we were training in PolyAI, we were training with batch sizes of more than 3,000 in order to get a loss function that was 1 out of 3,000 answer selection. And again, as I said, the best thing of it is not that you get a more informative loss function. It's that you can see much more data. It's much more efficient. Every batch takes much less time to compute. So basically, you can train things like in the Reddit dataset that I showed before and see several iterations on this data. The pre-computation, it's also very useful at inference time, because basically we will be able to imagine that we have a set that might have potentially hundreds of thousands of candidate responses. In a fully connected model, whenever we get a user input, we will have to compute the whole score of this input with each of the candidate responses. With a dot product, with a dual encoder dot product model, what we can do is we can pre-compute all our candidate responses because we already know which are them, and then whenever we get an input, we just compute the vector for the input. Again, we do a matrix multiplication, a matrix product, and basically what we are going to obtain is a vector with the scores for each of the candidate responses. We only have to pick the Rmax of the highest score there, and this is going to be our response. So again, this is really, really efficient compared with other models. So as I said before, recently we presented the PolyAI encoder, in which using this technique we are able to train dual encoder dot product answer selection model or response selection model, which it's able to do several iterations in the Reddit data, around I think 3 or 4, but most importantly, we get very good results in 1 out of 100 accuracy in the Reddit dataset, as we can see compared with other pre-trained sentence encoders or pre-trained models that have been trained not in conversational data but in text data. We are doing much better than them, mostly because we have mostly trained it in conversational data. Like for example, for this number for BERT, we have been fine-tuning BERT in this same conversational data, but it doesn't see, it only sees a fraction of the data that we are able to see with this model. But again, most importantly, the most important thing of this model is how efficient it is. We just train it during 18 hours in 12 GPUs, which compare with what it's going on nowadays with all the BERT and bigger BERT models. It's almost nothing. The training cost in a cloud computing service is under $100. That, again, if you check the cost, I think BERT, the original BERT, is estimated on being $7,000 or something like that. It's a model that runs fine in CPU, and it's very small. We could compress it up to 60, I think even less, to 40 megabytes or so. And as I said, it works better than these models in conversational tasks, but not only that, as I'm going to show after, it also works better in downstream conversational tasks. And yeah, this model, we train it just to be, let's say, single turn, just from, let's say, a single, the last user input to response, but you can easily extend it to include the context, the whole dialogue. Basically, you hierarchically combine the encoding of the last turn plus the encoding of the whole, like the last 10 turns or something like that. You combine them and you do exactly the same dot product scoring. So now I'm going to talk about, let's say, application of all these things we have been talking about to real-world tasks, which is basically or mostly what I have been doing during the last year and a half or so that I've been in PolyAI. So yeah, I've been talking like very good about retrieval-based dialogues, and I really think it's a very interesting path that is showing very good results, but is this enough? Does this already solve dialogue? Well, obviously not yet, because if not, we will see it in many more places. It might be good enough for some social chatbots or small applications and so, but task-oriented dialogue systems still require to have some kind of explicit state representation in order to interact with external sources. Like, for example, if we have an application to book a restaurant, we need to explicitly store like how many people is the booking for, when is the booking for, and also we need to somehow store the response that we need from the restaurant. This is not easy to do in all these latent spaces these models work on. But there is a lot we can get from these models or from techniques derived from retrieval. So the first thing is to use this model as an unsupervised pre-train for NLU task. As I'm sure that all of you are aware, unsupervised pre-training for NLP tasks has improved this task crazily during the last couple of years, so that you're familiar with Elmo, GTP, BERT, and all the things that have come after that, where basically what you do is, yes, pre-train a sentence encoder on large amounts of text data, and then you fine-tune or you train a classifier on top of these models in smaller amounts of task-specific data. The problem of these things for dialogue is that these models are not trained on conversational data. They are usually trained in text data. So basically they learn from a different distribution. They are trained mostly on language model losses. And again, these models are not evaluated on conversational tasks. If, like, for example, the glue tasks are mostly other kind of NLP tasks. The only thing that I think it's kind of more relevant for dialogue are the semantic similarity tasks, and I think that it only has one or two. So, well, as I already started saying, so there are differences between pre-training one of these models as a language model or as a response selection model. Again, like language models are trained on text, what response selection models are actually trained on dialogue, on conversations. This makes the response selection models learn representations about conversational clues, about, let's say, relations not just between words, but between the answer and the response, learning to basically it encodes the full sentences and basically finds the similarity between the sentence itself. And as we saw, these models are directly applicable to retrieval-based dialogue, so these models are directly applicable to dialogue tasks. But furthermore, we can use these models, we can get part of these models, use them as sentence encoder in order to learn downstream dialog tasks on top of them. Like, for example, intent detection. In this example, so what we did is to pre-train. This is exactly the same model I showed before, in which we pre-train a response selection model, a dual encoder model with dot product loss. And then after this has been pre-trained, we get, let's say, the self-attention layers. We train a small classifier on top of it. We don't even fine-tune these hyperparameters. And we just do intent classification, so basically semantic meaning classification of natural language on a small data set on top of this. And we got very good results. So basically we compare it with BERT. We mostly get in a few data sets that we tested with banking, e-commerce, and some FAQs better than BERT, usually slightly better than BERT. But most importantly is that in few-shot intent classification, we saw that the less data we were using to train these intent classifiers, the better the models trained on conversational data were doing. So basically this, the low data setting represent, like, I think it's a task where it has like 90 different intents, and we are using maximum 10 examples per intent. And in this case, the dual encoder model works much better than the other two that we compare with. This is very useful because, like, as Paweł was talking before, one of the biggest problems of collecting data is collecting task-specific data. This is usually very expensive. You have to clean the data manually. You have to, well, basically, yeah, it takes a lot of work. So the better we can do with these kind of models, the more we can take from the large amounts of conversational data that it's out there in order to pre-train these base conversational models, the less work we will have to do later in order to collect data to solve all these tasks. And again, as I said before, it's not just that it works better in low data setting, it's also that it's much cheaper and much faster to train. So in these experiments, what we compare with BERT large, is not just, obviously we didn't pay for the pre-training of BERT because this is already released there. But for example, the training time is much longer, basically because with BERT you need to fine-tune all the parameters, while in the other two examples we just needed to train a classifier on top of the fixed encodings. And as you see also, the model size is much smaller, so this is much more useful for real applications where you have to have several of these working on parallel and so on. This is also not only applicable to intent classification. This is an example how, like, value extraction. So basically a system that proposes the span of, for example, what I want to book a table for 8 p.m., a system that proposes the span for 8 p.m. If we train it on top of this encoder instead of training it from scratch, we learn much faster and better F1. And then this slide is just an example. I find it very interesting because, as I said before, we are training the encoder model in response selection, which is a different task to intent classification. No, but we can see a very strong correlation, like how when we improve the scoring 1 out of 100 accuracy in the response selection model, we always improve the accuracy in the downstream tasks, in this case in downstream intent classification. So now I'm going to talk about a different, by the way, how much more do I have? 20 minutes, okay. Probably I will finish too soon then. I'm going to talk about a different application of retrieval-based dialogue. So this is, as we have been explaining before, let's say traditional dialogue, traditional entity search, or usually restaurant search, which is what most of the people does in dialogue research, it's based on very well-defined ontologies and very rigid ontologies. So for example, DSTC 2 and 3, they have like a set of slots that you can just give a set of values and the user cannot say or cannot search for anything outside these slots. This is obviously constrain the dialogues and create fake dialogues. I mean, the user cannot ask the way he will ask in a normal restaurant. It has to know what it can say to the system in order to look for the restaurant he's looking for. This also requires a lot of special annotations. Usually the annotators need to understand how to tag each slot and so on. So this is very, let's say, annoying. And while some slots are obviously necessary, so for example, if you need to book for a specific number of people, you need to explicitly store this number of people. Usually the slots that you need to make some action, like a booking action, are necessary. That slots that you need to search or so on might not be so necessary. So, for example, what we could do is we can, for example, scrap from the internet, from some place like Yelp or TripAdvisor, all the reviews for restaurants in a city. So we will have a set of reviews, each of them has an associated restaurant to it, and then we are going to treat dialogue as a search over those reviews. How? As I said before, like the encoder model that we presented before basically maps all this natural language into a continuous space that basically represents the similarities between the semantics of these natural language inputs, which in this case are reviews. So basically what we can do is encode the reviews of each restaurant into this space. We are going to, basically they are going to be, let's say, like, we are going to treat them like as responses in this space. Each of the restaurants will have a different set of associated responses, and then when the user asks for something, like for example, I want a cheap place to find authentic sushi, we are going to map this query into the same space through the same encoder, and we are going to see, using some kind of heuristic, which reviews are close to the query that the users say. Basically, this is going to mean that if several points of a single restaurant are close to the queries of the user, that this is a restaurant that matches the user needs. So, as an example, we can see here how the user says, I want a bar with a good craft beer, and how the system has found 2 reviews that match, so basically 2 reviews of 2 different restaurants that match this query. So basically it has reduced the search to 2 restaurants. One of them says like serves good craft beer, and the other one says something about beer too. But the point here is that obviously there is not a craft beer slot. The system is not explicitly getting, okay, the user looks for craft beer, I go to a database, I see which restaurants are actually doing craft beer. No, this is being done totally in this semantic space that the encoder is creating. So basically, any of this, you don't need any of the slots for search that, for example, was used in the STC2 and 3 in order to do this. So, well, I think we have tomorrow or the day after a demo on this system. Feel free to come and try it. And yeah, finally, these were some slots that I actually just put in order in case I had to fill a bit of time. So I think that one of the things we learned at PolyAI when we were building task-oriented systems is that usually the bottleneck or the biggest problem with building all this system is the NLU. What does this mean? That as the NLU as the first part of the dialogue pipeline basically determines if the dialogue is going to work or not. You can have a very well-done policy, very well-trained policy, a very good working NLG, that if the system doesn't get what the user is doing, the system is not going to work. And probably NLU is one of the most difficult tasks here. So basically, the state of the art on the NLU will make us create like NLU that can only handle very small scope dialogue systems, which usually means that as the scope of the dialogue system is so small, for policy and NLG, it's usually enough to have, let's say, a rule system or template-based system for these 2 modules. This doesn't mean that that retrieval-based dialogue cannot give anything to let's say, to pre-trainings of policy learning or energy learning, no? So, for example, this has not been applied, but this is just an idea that technically the multi-turn encodings that we get with one of these sentence encoders could be technically treated as dialogue state. One of the problems that reinforcement learning has had during many years is that as the dialogue state was defined by the ontology, which was actually discrete, it was very difficult to find similarity in between different dialogue states. This meant that the policy had to see many turns and many dialogue states in order to learn how to act in each of them. If we can use one of these encoders to map the dialogue state in one of these continuous space, this might help reinforcement learning algorithms to learn faster. Again, also with ranking, NLG can also benefit a lot from ranking. So what we can use, for example, is like one of the problems of template-based NLG is that it's very rigid. It makes things like very unnatural or annoying for the user. If we can, for example, oversample NLG with a template-based method or even with a generative method and then rank it through retrieval-based dialogue in order to select the best response there, this could also give benefits to task-oriented dialogue systems. And yeah, now Paweł is going to go with the conclusions.
So I have this ungrateful opportunity to conclude. So don't sign me on that. A couple of thoughts worth, I guess, remembering as a takeout after this tutorial that we want to, I guess, send it to you is that pre-training, of course, is the future. We truly only started experimenting in last basically 2 years, 1 year. So we're not really sure how to use it properly. But both cases for response, retrieval, and for end-to-end systems, we start seeing already big signs that that's the way to go. And ironically, we talked a lot about the data collection paradigm. But again, I want to say that that the pre-training kind of changed the paradigm because it's at this point it's more about getting the good quality and well-defined data that are good for your particular case rather than the size of it, because all the stuff related with the basic knowledge of the language is kind of being trained during the pre-training phase. However, challenging data sets is still an ongoing process. I love the fact that in last 2 years, we see the pattern that basically in all NLU tasks, and EMNLP especially, we are giving new data sets, but we still have a lot of things to learn and do in order to get proper data for specific case in terms of task-oriented dialogues. The other things that we always forget about in some sense being overfit to English or Chinese is the fact that we don't really do a good job in terms of other languages. And if just looking at this graph in terms of top 10 languages in the internet, of course, there is a lot of traffic related with English and Chinese, but there's quite a lot of other languages that we don't really cover with. So if I'm often asked from people who are deploying some production level models in different languages, what can they do about it? And the answer is usually not really much, except for automatic translation to English. That's pretty much the state of the art in 2019. Which is a little bit disappointing, but there is still some work going on in this direction. Finally, just general again summary: deploying task-oriented dialogue system 2019. It's from our perspective, pre-training is a must currently to assure that the models are robust. Because the amount of data that these models see is way bigger than the fine-tuning phase. Second of all, template-based NLG is still a standard approach. So there's been a lot of work trying to make it through neural architecture, but in reality, template-based is way safer approach. As Iñigo said, response selection can get you far, but at the end of the day, you gotta, at least in task-oriented dialogues, at the production level, you gotta call third-party API calls. So we need to think about how we can incorporate that in just response selection process. And finally, end-to-end systems have a long journey to go in terms of make them possible to deploy. Personally, I don't see how we could deploy end-to-end system for big clients where robustness is a top priority. But I think in terms of the possibilities of deploying them on for smaller clients, it's definitely doable in the next couple of years, but there's still a lot of things to work on. So again, thanks for coming for a tutorial. We have a couple of more minutes for all the question, comments, ideas. And we gonna, as I mentioned before, I guess I will leave the slides. Well, there's a lot of slides. It's not gonna be easy that way. I will leave the slides with the slides, with the link for the slides. Sorry, keep thinking and talking at the same time. Sometimes it's hard. That will be updated in a couple of days, where you can download it and go through again for the whole presentation. Thanks again for coming, and we welcome all the questions. We're just conversation after the tutorial. Anybody? Oh, yeah.
Hi, thank you for the great tutorial. I have a question about the first step, about the data collection. So you mentioned that the data is very noisy. Do you have any methods to measure the data quality in different aspects?
In terms of what comes to my mind is what the easy way to see how noisy it is basically training, for example, in Wizard of Oz fashion. For example, you train belief tracker on top of the data that you have and basically see how good it is. And then just checking the prediction that your belief tracking is doing versus the annotation that you got. And if you see that the number is super low, that basically means that that you learn some patterns and out of nowhere on the test set you have a lot of noisiness in terms of the label. So that will be a quick information that something's going wrong.
So it means you can only check the data quality after the training, right? So that's
I mean, standard approach is literally setting up the traps for mTrukers. That's the other thing. Well, basically doing something horribly wrong in terms of the setup and checking whether either Turkers are reporting that or they're they can do something about it. Yeah.
Cool. Thank you.
Yeah. But the fights with mTrukers never end, so yeah.
Okay, it's work. Thank you for tutorial. As I understand, you done your own BERT that faster, better, and smaller than original.
Better model than
your own BERT model.
BERT, yeah.
Faster, better than original. Am
well,
I right?
better for the task that we care about. Yeah.
And can I or somebody from this auditory take your BERT, your version, and train our own data sets?
It's a really good point. So all the data sets that we're using are all available online. We published one paper at ACL last year about the model that we are actually using. We're thinking about, just to be sure, I think we will deploy not maybe the code, but the weights so that you can...
weights without code? So I need to...
from the clouds, basically for at the inference level, so you can call it and see how it performs for your tasks. Yeah.
So I can take your code and try to train a language model on my own data, or not today?
Yeah. No.
So as far as I know, for now we are only going to release the weights of the encoder. So basically we are going to release a pre-trained encoder with which you can get those encodings. So if you are going to train something on top of these encodings, you can. If you want to, let's say, retrain the whole encoder model, I don't think so.
So I can do inference but not train?
No, you can't do train. Sorry. So all these results I was showing there, you actually don't change any weight of the pre-trained encoder model. You just train something on top of it. You put a few layers on top of the encoder model, and you train just these layers. So you can do that with your own data. That's doable. What you cannot do is train all the layers or retrain all the layers of the model.
Okay, maybe after all questions, but I can just maybe unfreeze on layers and train all layers. I don't know.
You can train something on top.
Hi, thank you for the tutorial. I have two questions about the first part about data collection. So, how the DST, the dialog state tracking, is used in the task? Because I think there was a slide where you were showing the probabilities about the belief, but I could not understand if the probabilities are changed during the...
So you're talking about how after data collection we can use it for dialog state tracking, yeah?
Yeah.
Yeah, so if you, for example, in M2M it's pretty obvious in terms of Wizard of Oz is a little bit hidden, but if you think about it, what we're doing at this stage when we're gathering the data set from the system point of view, the moment that the mTurker is putting something into database GUI, that basically we are saying that these are the slots that current belief tracker should predict to at the current stage.
So it has the history of the...
Well, the history is that in this case is mTurker who sees the context of the dialogues. He sees that the user currently is looking for a ticket train to, for example, London, and he will put London as a destination place. Yeah.
And the second question was about, I mean, you were listing, your colleague was listing several conversational corpora.
Yes. Mm-hmm.
And they were all asynchronous data. So I understand you didn't want to speak about automatic speaker recognition to transcribe, let's say, meetings or phone calls. But I think there is only 2 or 3 corpora, AMI and ICSI, and another Russian corpora that they were like transcriptions of conversations, spontaneous conversations. But I think the gathering the data is not very hard, but actually gathering the data in a way that I mean you protect the data.
The anonymity of the users, yeah, it's hard.
Yeah, exactly.
Yeah. Transcribing the speech data is a problem on its own. Yeah.
So is it like a choice for you to work on asynchronous data, or because synchronous data, for example, online chats with the humans actually on some websites, and I'm working actually on the stack corpus, that is chats from sessions from the Settlers of Catan game, and it's actually annotated for discourse analysis. So is it a choice for you to choose asynchronous than synchronous?
Well, at the end of the day, it's all about the scale. So as long as it's big, we work on that.
I see. Okay, thank you.
Simple as that. Yeah. I was not expecting from Andy.
Thanks for a great tutorial, Paweł. And the simple question. What kind of user behavior, from your experience, you observe in the dialogues that you think that is very hard to tackle? For example, like negation, or for like change of user goal, something like this kind of user behavior. You think is that hard to tackle?
Yeah. So
and is it covered in the public? So in terms of research, is it already covered in our data sets?
Ironically speaking, the hardest challenge that you have during the production is the fact that a lot of people don't want to talk to the chatbots in the first place.
Okay. Right. Okay.
Yeah. The second part, I guess, it's totally dependent on the domain that you're working with. Yeah, and then demographic, which comes back to the fact that, for example, old people are way harder to create a system for than for example, the younger generations. Yeah.
Okay.
Yeah.
One of the things we find more difficult in here is as soon as something in the dialogue goes wrong, the users start becoming very confused, and usually the dialogue goes to a disaster. So usually it's as long as the dialogues go through a happy path, sometimes they work surprisingly good. It's very difficult to recover once something started to go wrong, once the user doesn't understand why it says 3 people if he has said 3 p.m. That's when it's very difficult to get. So let's say it's very difficult to understand when the user wants to recover from something that has gone wrong. Picking things at the first time, it's usually kind of good and straightforward. As soon as the user is corrected something, that's where it becomes quite challenging.
I see. Thank you very much.
Thanks. I might have missed it, but once you deploy your systems to the client's environment, what do you do to use the new data that people are playing with your chatbots or whatever and merge it with your gathered data in either way that you have gathered it?
Yeah, so it's a good point. It goes back to the data collection paradigms. We did not cover, except for mentioning the STC2 human-to-machine data collection. I was already asked that before. The reason is that there was so much to talk about that we didn't have just simply time. But most of the time, from research also perspective, you never even have a chance to get this data. So from an industrial perspective, we just I guess the answer is, again, straightforward. In a sense, we're trying to log down everything that we can do in terms of the behavior of the system, and try to find the main metrics that breaks down the conversations. And given this, we can start basically spotting the crucial points of the behavior of the system that are completely destroying the conversation, and start working towards well, making it better. Yeah. Looks like it's all. Again, thanks for coming. If anyone wants to talk afterwards, please go ahead and chat with us. Thanks for coming. Bye.